Welcome back, everybody, to the 1937 Nobel Prize in Physics. This time we learn a little bit more about the electron. So remember, one of the things about scientists is we're trying to study nature, we're trying to study the world around us, we're trying to really understand everything down to the subatomic particle level. The more we know, the more we can do with it, the more we can hand to engineers and say, here, we've got this cool thing, you go figure out what to do with it. And the electron turned out to be pretty useful because without it, we wouldn't have electronics, we wouldn't have CCD cameras, we wouldn't have any of the stuff that allows me to communicate with you. So we like this stuff. But the electron, this time we're going to learn a little bit more about it. So two people shared this prize. It was a joint prize for one project. Clinton Davisson and George Thomson. What they did was they ran an experiment that allowed you to do diffraction of electrons through crystals. And we'll figure out what all that means in a minute. So remember, much more about electrons this time. More than just like, hey, what do electrons call their friends, which is typically currents. Sorry, physics joke there. I won't give up my day job. But let's dive into what this really means. A little bit of history here before we get too deep into this experiment. The gentleman on the right is Clinton Davisson. The gentleman on the left is George Paget Thomson. Thomson's father, actually J.J. Thomson, won the Nobel Prize in 1906 for, shockingly enough, the electron. So there's a family history here of working with this one particular particle and winning Nobel Prizes with it. Now, the other thing that happened was these two gentlemen actually did this work separately, but came to the same conclusion just about at the same time. So that wound up as a joint prize. Now, the other interesting thing is this actually verified all the theory work done by de Broglie, who won the prize in 1929. So there's a long history connecting multiple previous prize winners and this particular experiment, which I think is pretty interesting stuff. Now let's look at exactly what they did. Now both these labs were using essentially the same experimental setup, and for years had struggled to really kind of achieve what they were looking for because they weren't reaching a low enough level of vacuum. So that problem had to get fixed before they could actually go on to do this experiment fully. But technology was advancing, things were getting better in the science labs, and it was coming a long way. Now, Clinton Davisson was working along with his assistant Lester Germer at Bell Labs. And Lester Germer kind of got the Walter White honorable mention award here because he was an assistant, and assistants rarely win the prize. But what they were doing was firing slow-moving electrons at crystal nickel targets. And the angular dependence of the reflected electrons was measured. So you get some intense electrons at one spot and some less intense electrons at a different angle. So that angular dependence really matters. And what that was determined was they were seeing a similar diffraction pattern as those predicted by Bragg for X-rays, which we talked about Bragg a while back, if you've been watching these videos. Now, it did have some small but significant differences from X-rays, and those were due to average potential, which in the electron is a little bit different than what you find in the average X-ray. And Hans Bethe went on to show that in more complete analysis. Now, Hans Bethe, the first time you've heard that name, but he went on to win the Nobel Prize in the 60s, so we haven't heard the last of him yet. He was actually instrumental in some other stuff, and we'll get to him later. But at the very same time as Davisson and Germer, George Thomson and his student Alexander Reed were independently demonstrating the very same effect, firing electrons through instead of reflecting off of celluloid films to produce the same diffraction pattern. And what that allowed them to do was to share the Nobel Prize by getting to the same answer from two different methods, which is actually really cool. That's what you want to see in science, is be able to get the same answer in multiple different ways. You don't want to be like, well, you have to have exactly this lined up with exactly that. You want the answer to be the answer. You don't want the answer to be conditional. And that's why things like this are important. So why is all this important? Yes, it shows the wave particle nature of electrons, but who cares, really? Why does it affect your life? Well, we've all lived in a world for a while now where we hear about advanced materials and advances in this and advances in that. And one of the things that made a lot of news for a long time was nanoparticles and nanotechnology. It was going to change the world. And in ways, you're actually using nanotechnology now. You don't even realize it. which is exactly what you want from a piece of technology, for you to have this whiz bang thing and not realize that you're actually using something as just star spangled crazy impossible as it is. Now, nanomaterials in particular wouldn't necessarily be all that possible to understand in a laboratory sense without things like X-ray diffraction or electron diffraction or all these other scientific techniques that you see. So what's happening here is we're building a groundwork for equipment and techniques that are going to lay pave the way for future advances in material technology and engineering. Now, why does material technology matter, right? So think about your grandparents' kitchen. They had these huge cast iron skillets. Now we have more advanced materials. I still use cast iron, but it's not the same cast iron as my grandmother had. Now, we have lighter weight cars that are just as safe. We have spacecraft that can do more than what we'd be able to in the past with higher levels of safety. All these advanced material things actually do matter to our daily lives. And without these sorts of techniques, those materials might not have ever been developed. So thank you for paying attention through this one. I know this one's a little bit kind of creepy science in the lab stuff, but it really does matter. Without it, you don't get to have these advanced materials we see today. So it does do more than that. But it's a great bit of fundamental science here that kind of does make a change. So please don't forget to click subscribe on the channel, click like, and hit the bell icon for updates as they come along. And we'll see everybody on the next video.